Hello everyone, welcome to the channel. I hope you all are doing great. So we were discussing about our previous year questions of the UPSC Geoscientist exam, and in that we have started with the physical chemistry portion. Previously we have discussed the chapters that was your KTG, thermodynamics and solutions and conjugative properties. These three units we have discussed where from the past, that is from the year 2020 to 2025, your each and every single question it was discussed. Now in the similar way, the next chapter that is your electrochemistry, for this also the past all these years, that is from 2020 to 2025, each and every single questions we are gonna discuss. Okay, so if you have not watched the previous chapters, playlist is there on the channel, you can check that. Or I'll also provide the link in the description. Even from that, you can get the access for that. Also, the organic chemistry portion we have already covered, so you can have a look for that as well. Okay, so let us begin with the solutions to this one. Before starting the video, if you are coming to the channel for the first time, make sure you subscribe to the channel and do hit the like button also for the video if you understand the concepts, and do share it with your friends as well. So let us begin with this particular chapter. So the first question is there on your screens. It says the equal volumes of what concentrations of the AgNO3 and the HCl it should be mixed to form the AgCl precipitates. Now what you have to form is the precipitates of the AgCl we need to form it. Now you can see here the KSP of the AgCl is given to us, which means the solubility product is given to us. Precipitate formation will be there only when the ionic product, it is gonna be more than that of this solubility product value. Okay, so we are forming the precipitates by mixing the AgNO3 and the HCl. So AgNO3 is gonna give you the Ag positive and the nitrate ions, whereas HCl will give us the H positive plus the Cl negative, right? So what we need is now we have to form the precipitates of AgCl. So for that we need is the concentration of Ag positive and we need is the concentration of the Cl negative. That is gonna come from the concentrations of this AgNO3. You will be getting the concentration of Ag positive, and from the HCl we are gonna get the concentration of our chloride. Now from the options you can check it and find the ionic product. If you, and check that if it is more than the KSP value or it is less than that, based upon that the PPTs it will be performed. Okay, so let us begin with this. The first option we are having the AgCl. AgNO3 concentration is 10 raised to the power of minus of 4. From that, the Ag concentration you will be getting it as 10 raised to the power of minus of 4, and Cl negative it's gonna be 10 raised to the power of minus of 7, which we are getting it as 10 raised to the power of minus of 11, and this value is less than the KSP. That means no ionic product formation it will be there. Next option if you see, Ag positive concentration is 10 raised to the power of minus of 5, and for the Cl negative it's 10 raised to the power of minus of 6, which is coming out to be 10 raised to the power of minus of 11. Again it is less than the KSP value, so no PPTs it will be formed. Next is option C if I see. So this is the option C. In this, the Ag positive concentration it's gonna be 10 raised to the power of minus of 6, and for the Cl minus also 10 raised to the power of minus of 6 you will be having, that comes out to as 10 raised to the power of minus of 12. Again this is less than the KSP value, so no PPT formation is gonna be there. In the option B if I check, Ag concentration it's gonna be 10 raised to the power of minus of 4, and the Cl minus concentration will be 10 raised to the power of minus of 5. It's coming out to be as 10 raised to the power of minus of 9, which is more than the KSP value. That means this is the scenario where the PPT formation is gonna take place because our ionic product is more than the KSP value. So the correct answer will be the option D in this case. Okay. Moving upon to the next one. we have is this question. The solution product, that means the KSP, again it is given. For this particular salt it is given to us, its value is this much. What is the concentration of this anionic part in this? So if you see this salt, that is Ag2CrO4, it's gonna facilitate the ions which will be 2Ag positive plus of the CrO4 2 negative, right? So we need to consider the solubility product for this. So if S is the solubility for the Ag positive, where the 2S will be the solubility because stoichiometry will be included, and for the CrO4 2 negative, the solubility will be the S over there. Now, if I write the KSP for this, it's gonna be the concentration of the ion, which is of the Ag positive, raised to the power of its stoichiometry into the metan concentration it will be there, right? Now for the Ag positive, we have is 2s, it will be raised to the power of 2, and for the CrO4 2 negative, we are having the solubility as S. So this comes out to be as 4s cube, and its value is already given to us, which is 32 into 10 raised to the power of minus of 12. So we are getting here as S cube as 8 into 10 raised to the power of minus of 12. Solving this, the solubility value you will be getting it as 2 into 10 raised to the power of minus of 4. That is given to us in the option A over there. Okay, so A is the correct answer in this case. Moving upon to the next one, we have is this question. It says the cell constant for a zero point 0.1 normal PCl solution, it is found out to be 0.98 centimeter inverse. Cell constant means length upon the area, that is when you are carrying out the electrolysis or the electrolyte cells that you are taking, the distance between the electrodes ratio of this distance between the electrodes, which is denoted with the length L, and A is the area of cross section of that electrode. The ratio of this length to the area, it is called as the cell constant. Its value is given to us, that means it is 0.98 centimeter inverse. Okay. The resistance offered by this much normal solution of the HCl, it is this much. So resistance value it is given to us as 89 ohms. This is for the another solutions, the resistance value, that is 89 ohms we are having it. What is the specific conductance for the HCl solution? Now in the same beaker you are, or the same cell, the experiment you are carrying it out, so the length to the area ratio, which is your cell constant, it's gonna remain the same only. So initially for the KCl, they have taken and using that they measured this cell constant value. Now they are taking this the HCl solution. For this, the resistance value it is given to us. Concentration is different. Solution is all in fact different, but the resistance offered in that case it is this much. So since the cell is the same, as I said, the cell constant is gonna remain the same only. We know that R is equal to the rho L by A, right? Where rho is the resistivity, R is the resistance, and L by A is the cell constant. Now we are given the resistance value. We need is to find the specific conductance. So kappa we have to find it out. Kappa, which is equal to your 1 by rho value, that is gonna be equal to 1 by R into the length by the A of it. Alright, so just substitute the values 1 by 89 ohms into the the cell constant value, which is 0.98 centimeters inverse. Right? This is the value we are having. So just solve this. The answer we will be getting it as 0.01101. It's gonna be ohm inverse centimeter inverse, or we can write it as 1.101 into 10 raised to the power of minus of 2 ohm inverse centimeter inverse. The answer you are having is the option B in this case. Right? Now, moving upon to the next one, we have is this question. It says, what will be the correct order of mobility of the following alkali metals in the aqueous solution? Aqueous solution means the water is present in this. So here the ions we are having is lithium positive, sodium positive, the potassium and the rubidium positive. All of these alkali metals they differ in their sizes. Here you compare the if you compare the sizes of this in the without solvation if you are comparing, this is the size without solvation. Without solvation. Here the rubidium positive we think it is gonna be it's of the largest size we are having. But here the rule of the aqueous solution it comes into the play. The one that is of the smallest size, the ion which is of the smallest size, it's gonna have the high charge density. It has high charge density. So due to that, what is gonna happen? This is gonna be hydrated by the solvent molecules to a larger extent. So here you see, this is of the small size lithium positive ions you are having. So the aqueous solution, which is the water molecules, due to the dipole difference that is present between them. So this interaction between them it is present. So due to that, this lithium positive it's gonna be hydrated. A large number of the water molecules is gonna surround this like this. So since it has the more charge density it is having, so it's gonna attract more number of the water molecules towards itself. That means its size in the aqueous medium it's gonna be the maximum. Whereas the rubidium positive that you are having, it's gonna have the least charge density. It has the least charge density. So lesser number of the water molecules will be coming towards it. So its size in the aqueous medium it's gonna be the least. So with the solvation, the sizes if you see with a solvation, the sizes if we compare, the lithium positive it's gonna have the maximum, followed by the sodium positive, then the potassium, and least is gonna be of this rubidium positive. Right? Now, mobility. Mobility means the speed with which it is moving. Mobility. Mobility it is dependent upon the size of these particles, these ions now. More is the size, lesser will be its mobility. Right? Mobility is inversely proportional to the sizes. So here you see lithium positive in the hydrated medium it is having the highest size it is having. Right? Because of its high charge density. So its mobility it's gonna be the least, followed by the sodium positive. Then we have is the potassium positive, and maximum will be for the rubidium positive, the mobility you are gonna observe it. So this is gonna be the order that is given to us in the option B and E. It is given us to be the same only, rubidium, potassium, sodium, then the lithium. So might be some order correction might be there. So you can mark any of them. So I am considering the option B as the correct one. Okay. So the main concept is this only, that is based upon the charge density that is dependent upon the size of these ions that we are having. Right. Now the next question we have is this one. It says during the electrolysis, that means the current is being passed through the silver nitrate solution. Loss in the anode compartment is this much. In the voltmeter connected in the series, 1.259 grams of the silver it was deposited. So what would be the transport number of the two ions? Okay. So for this, you see AgNO3 we are having. In this, the current is being passed, which means it's gonna facilitate the ions Ag positive and the nitrate ions. So cations, they are gonna move towards the cathode, and the anions they will be moving towards the anode. And at the cathode your reduction it will be taking place, and at the anode the oxidation it's gonna take place. This is what is happening. So now we are given that at the anodic compartment this much amount of the loss we were having it, and at the this anodic cathodic end this much amount of the silver it is getting be deposited. Now to find the transport number of the cationic species which is getting being deposited, that I am denoting it as metal with the positive charge, this is equal to the ratio of the number of the gram equivalents of the metal, that is your silver ions, which is lost, at the anodic compartment upon the number of the gram equivalents of the metal ion which is deposited. This ratio it gives you the transport number. Now we have been given that this much amount of the metal was being lost, which is 0.589 grams, 589 grams of it. So this much is the weight which is being lost upon its equivalent weight will give us the number of the gram equivalent weight of the Ag positive is the 108. Now in the denominator, number of the gram equivalents of the metal which is being deposited, that is given weight 1.259 upon its equivalent weight which is 108 grams. So this is gonna give you the transport number value which is gonna come out to be as 0.468. This is the transport number for the Ag positive ions. So the transport number of the Ag positive, we are getting it as 0.468. Now also we know that transport number of the cationic part, which is your Ag positive, plus the transport number of this anionic part, this sum it is equal to be unity. Right, now we have calculated the transport number of the cationic part. For the anionic part, we can easily solve this by subtracting it from the 1 minus 0.468, which is gonna come out to be as 0.532. So this is gonna be the transport number for the anionic part. So you can mark this. This one is for the Ag positive and this one is for your nitrate. So the answer we are seeing is the option A only, 468 and 5. So A is the correct option. The direct formula you can just remember this one, that is based upon the number of the gram equivalents of the metal which is getting being lost to the number of gram equivalents of the metal which is being deposited. This ratio is gonna give us the transport number of that metal. Okay. Next one we have is this question. It says the molar conductivities of this KOAC, that means this salt, and the HCl at infinite dilution in the water at 25 degrees centigrade are this much and this much respectively. To find the molar conductivity of this acid, that is your acetic acid, at infinite dilution, the additional molar conductivity value of which one of the following electrolytes will be required. So here you have this KOAC we have been given, and along with that the HCl is given. We need to find this of this HOAC. So that means H positive ions we need and this acetate ion we need it. So that H positive ions we can get it from the HCl, right? From the HCl you will be having H positive and the Cl negative it will be present, and the OAC negative we can get it from this KOAC value, that is potassium acetate. So K positive and the OAC negative value. Now from this we need to subtract the additional ions that we are getting, which is my Cl negative and this K positive. That means this K positive Cl negative ion, that is of this KCl, KCl electrolyte, this conductivity we need to subtract it from the total so that we can get the conductivity of this acetic acid, right? So that means these values we already know it. This one is the additional one that we need the conductivity of this one. So the additional molar conductivity value of this KCl is needed over there. So the correct answer will be the option B in this case, right? Moving upon to the next one we have is this question. It says what will be the effect of the dilution on the specific and the equivalent conductance of the aqueous solution of a strong electrolyte. So we know that the equivalent conductance that we have, it is equal to kappa upon the normality of it. Normality is number of the gram equivalents of the solute, gram equivalents of the solute upon the volume of the solution. So that is gonna go in the numerator, volume of the solution. In the liters you need it, here the kappa is as it is. So here they are saying we are diluting it. So with the dilution, the volume of the solution it is gonna increase, which means the equivalent conductance it is gonna increase, right? So with dilution, the equivalent conductance it is gonna increase, right? Whereas if you observe with the dilution, the specific conductance that you are having, it's gonna decrease. Reason for that is specific conductance means in a particular volume how much ions you are having. But here with the dilution, the number of the ions per unit volume it's gonna decrease, which means the specific conductance it is gonna decrease. Right? So it is gonna be decreasing with the dilution because the number of the ions per per unit volume it decreases. Right? So kappa is gonna decrease, specific conductance it decreases and equivalent conductance it increases. That is given to us in the option A over there. Okay. So now the next question we have is this one. It says the mean ionic activity coefficient which is denoted as gamma plus minus, while the cation and anion are denoted as gamma plus and the gamma minus respectively. The correct relation amongst them given that mu positive and the mu negative are the number of the cations and the anions in it respectively. So salt we are having is of the type where the metal its number is mu positive and the anionic part that is suppose X you are having its number is mu negative. When it's dissociating, it's gonna give you mu positive number of the metal ions, which is gonna have the charge of mu negative, right? And the X number, that is the anionic number, it's gonna be mu negative, X negative charge, negative will be there, and this charge present on it, it will be of the mu bar we will be having the charge, right? So here if we want to write the mean ionic activity coefficient that is gamma plus minus, here all of this it will be raised to the sum of the stoichiometries of this cationic as well as this anionic part that is mu positive plus of the mu negative it will be there. This is equal to the activity coefficient that is of the cation raised to the power of its stoichiometry into the activity coefficient of this anion raised to the power of its stoichiometry, right? So this gamma plus minus, we can write it as gamma plus, which is raised to the power of its stoichiometry, gamma minus raised to the power of its stoichiometry, and this whole. Now this power that was in that is present over here, this one we can shift it on this particular side that will be going like this, which is the sum of mu plus of the mu minus of it. So this is how the mean ionic activity coefficient gamma plus minus it can be written. So the correct answer is the option B in this case. Alright, moving upon to the next one we have is this question. It says the specific conductance of a 0.01 molar solution of acetic acid. It was found to be this much value it was having it. Okay. The molar conductance of the acetic acid at infinite dilution it is also given to us. Okay. What is the degree of dissociation? That means the alpha value we have to find it out, which is a ratio of the molar conductance at any other conditions to that of the molar conductance at infinite dilution. This is the ratio we have. Now to find the lambda n, that is at 25 degrees centigrade, that is the given conditions and this much molar concentration when you are having, this is equal to the kappa upon the concentration of it, right? So here now the kappa value we are having it as 0.015 upon the concentration it is already given to us in the molarity which is 0.01 molar. Solving this, the value you will be having it as 15 into 10 raised to the power of minus of 4. So now alpha value, it's gonna be lambda n upon the lambda n at infinite dilution, which is 15 into 10 raised to the power of minus of 4 upon the given one, which is 400 into 10 raised to the power of minus of 4. Units are the same, Siemens meter square per mole inverse. Here also it was the molarity, it was there, that is mole per meter cube you were having it, and its units were meter inverse, it was given to us. So its units when you will be solving it, here the Siemens meter inverse it will be there. So its units we will be getting it as Siemens meter square per mole inverse. The units are the same. Okay, so Siemens meter square per mole inverse. So solving this, you will be getting the value as 0.0375. So degree of dissociation is 0.0375. That is given to us in the option B over here. Okay. Now moving upon to the next, we have is this question. It says in a moving boundary experiment, which is having this much this many number of moles of the lithium chloride, the boundary in a tube with the cross-sectional area, that is this much, it moves through 8.1 centimeter, the length is given, and in time is also given, which is 1500 seconds for a current of these many amperes. What will be the transport number of the chloride ions? So in the boundary experiment, we have that there the HCl solution is taken. Now instead of the HCl, this time lithium chloride it is given. So as per the H positive formula that you have to get in the boundary experiment, the transport number of the cationic part, it is area into the length into the concentration into the Faraday's constant upon the Q, which is the charge over here. So A is the area of cross section, L is the length, L is the length or the distance that is given to us, C is the concentration, F is your Faraday's constant, it is Faraday's constant, and Q, it is the charge, which we can write it like this also, because we know that current, it is equal to the charge upon the time. So Q can be written as I into dt, the small q or the capital Q. This either way you can present the charge. This is equal to the I into dt. So this can be written as IT also, where I is your current, T is the time for which this current has been passed. Okay, so this is the formula which is used in the boundary experiment. So just substitute the values. So now instead of the cationic part, this is the H positive. Instead of that, you are having this the lithium positive. So that means here the transport number of the lithium positive we will be calculating using this formula. So just substitute the values now. The area is given to us 0.125 centimeters square. Length is given to us to be 8.1 centimeters of it, and concentration, which is given to us as 0.01 moles, it is given to us. Right? Now concentration, that means here only the mole number of moles are given, but we need is the concentration. So for that, we can write it as 0.01 moles upon the 1000 ml of it, right? Because ml is also 10 raised to the power of minus of 3. This multiplying it with the 1000, you are gonna get is the same value. So this is gonna come out to be as 10 raised to the power of minus of the 5. Okay, so just substitute this value 10 raised to the power of minus of 5, and the Faraday's constant value we have is 96500, that is charge of the 1 mole of electrons upon the Q, that is I into the T, it will be there. This is written as current into the time, because these are the values which is given to us upon 1.8 into 10 raised to the power of minus of 3. You can see this much current it was being passed, and the time is 1500 seconds, right? So this is gonna give you the transport number, and its value you are gonna get it as 0.361. So this is gonna be the transport number of the lithium positive ion. Now, for we need to find this for the chloride ions, right? So now the transport number of the lithium positive, plus the transport number of the chloride ions, it is equal to the unity. So transport number of the chloride ions, we can find it as 1 minus the transport number of this lithium positive, that is 1 minus 0.361, which comes out to be as 0.639. So this is the transport number of the chloride ions that we wanted to find it out. Okay, 0.639. So make sure you are doing the correct options, marking the correct options over here. You see, here it is transport number of the chloride ions. By using this formula, sometimes we just calculate it up to here. We are getting it as 0.361. You can see in the options this value is also given to us. But this is for the cationic part. They are asking is of the anionic part. So from the one, the subtraction is important over there. So make sure you are not making this mistake. Okay. Next one we have is this. It says when HCl it is titrated with the NaOH, the conductance at the end point is. So what type of the conductance curve we observe it? This graph basically we observe it. Here you have is the conductance value and here you have is the volume of the NaOH. So initially, suppose this is the beaker you are having. This is the beaker. In this, initially you are having is the HCl. Here is your HCl present in it, and you are measuring the conductance in it. So here the H positive ions are present. Due to that, the initial conductance is gonna be very high. You are gonna observe suppose this much conductance you are having. Now through the burette, what you are doing is you are adding is the NaOH from it. Here the drop by drop you start the addition of this NaOH. So with that, what is gonna happen? The HCl will be combining with this NaOH and we will be getting the formation of NaCl. Along with this, the water is getting being formed. So here this H positive, it's combining with the OH negative and the undissociated water is getting being formed. Also the H positive ions, which was initially responsible for the conductance, it is getting being replaced by this sodium positive, which is larger in the size, right? So its conductance it's gonna decrease. So we will be observing this type of the graph like this. The decrease in the concentration you will be observing. Now a point will come when the equivalence point you will be having. That means equal number of the moles of this HCl and NaOH will be present in this particular solution. After that, when you add the NaOH, the conductance it is gonna increase. That is because the OH negative ions, due to the Groth's mechanism, its conductance is high. So its the conductance value it is gonna increase. So the point where this equivalence point that we have achieved it, or the end point, that is this one, where the equal number of the HCl and the NaOH we are having it. So this is the point which is called as your, you can call it the end point or the equivalence point. Equivalence point. Okay. Difference is there between these two endpoint or the equivalence point. But for the while we can say consider that this is the same only. So when the HCl is titrated, what is the conductance at this particular end point? So at the end point when you are having, you can see the conductance value, it is the least in this case, right? So that means the minimum conductance value we will be having at the end point. Okay. Next is we have this. This is from your this kinetic this that was kinetics chapter it is there, but I have added it in this unit only because not much questions were there from the kinetics. There's only a single question it was there, so that too I have included it in this part only. Okay, so it says consider the following first order elementary reaction. A is giving us the B and B is going in the backward direction giving you the A product. The half-life period for the forward reaction and that of the backward reaction it is given. What will be the value of the equilibrium constant in this? So for the forward reaction you are having this. A is giving you the B. Rate constant is K1 for this. It is your first order reaction and for the first order reaction P half is equal to my 0.693 upon the rate constant which is K1 in this case. Right? Whereas for the backward reaction, that is B is giving us the A, the rate constant is K2. For this also T half value it is given to us, which is 0.693, but this time the rate constant is gonna be the K2 over here. Alright, so this is the T half for the forward reaction and this one is for the backward reaction. We need to find this the equilibrium constant, that is defined as the ratio of the equilibrium constant of the forward reaction upon the equilibrium constant that is of the backward reaction. So we need to find this K1 and this K2 value. So K1 you can write it as 0.693 upon the T half that is of the forward reaction, right, upon the K2 value which is 0.693 upon the T half that is of the backward direction. Right, so this we can write it as T half that is of the backward direction upon the T half that is for the forward reaction. Right, that is gonna be for the backward reaction T half value is your 1 minute and for the forward one it is your 10 minutes. So that means K equilibrium it's gonna be 0.1. Alright, so the correct answer will be the option C in this case. Okay, now moving upon to the next one. This question you are having. It says the specific conductance of a decimolar, which means the 0.1 molar concentration of this KCl it is there. At 18 degrees centigrade, it is 1.12 Siemens meter inverse. The resistance of the conductivity cell containing the solution at the same temperature it was found to be this much. What is the cell constant you are having it? So we know that R is equal to the rho L by the A, right? We need to find is the cell constant which is equal to the R upon the rho, right? 1 by rho, it is nothing but the specific conductance that is this kappa value. That means we can write it as R into the kappa value, right? So here this R value we are having, it's equal to the 55 ohms. It is your 55 ohms and the kappa value which is given to us as 1.12 Siemens meter inverse. So ohm and Siemens is nothing but the ohm inverse only. So these two will be getting answered out. You will be getting the cell constant in the terms of meter inverse. That is gonna be 61.6. This is in the meter inverse. If you check the options, it's given to us in the centimeter inverse. So meter just you have to convert it into the centimeter. You know 1 meter is small, 100 centimeters. It is 100 raised to the power of minus of 1. This will be centimeter inverse. So that means you have to divide it with the 100 which comes out to be as 0.616 centimeter inverse. That is gonna be your cell constant. So the correct answer is the option A in this case. Okay. Next is we have this. It says in the acidic medium, the MnO4 negative, it is converted into the Mn2 positive. The quantity of the electricity that is required to reduce this many molar MnO4 negative to the Mn2 positive will be. So MnO4 negative, it's getting being converted to the Mn2 positive. So here the oxidation state you can find it out. Here the manganese is in the plus 7. From the plus 7 it's going to the plus 2, which means the 5 electrons exchange it was there. Right? Now here if you write the complete balanced equation in the acidic medium, here the O4 it is there. So that means 4 water molecules it's gonna be produced and here the 8H positive it will be added. So this is the complete expression for this. Main thing is that these 5 electrons are involved in the conversion. So for the 1 mole, how many electricity would be required? That is of the 5 Faradays. 5 Faraday current it will be required since 5 electrons are involved in this conversion process. Now we need is to find for the zero point 0.2 moles. So for the zero point 0.2 moles, just the unitary method, it will be 5 into the zero point 0.2 Faradays of the current we are requiring. So this is gonna be equal to the 1 Faraday. That means this much amount of the current we are requiring for the conversion. So C is the correct answer in this case. Okay. Next is you have this question. It says what will be the correct order of mobility? Now similarly in our previous time it was the cationic species. Now for the anionic species in the aqueous solution the mobility is getting being asked. Same concept you have to use over here. So here if you compare the sizes, so based upon the charges if you firstly see the sulfate ions that is of the biggest size it is having without solvation if you are considering, followed by the bromine. Then you have is this fluorine and the next least is gonna be the fluorine. This is the sizes of these anions without solvation. Without solvation. So here again the concept of the charge density is gonna come. The one that is of the largest size, it's gonna have the least charge density. It has the least charge density. So that means it's gonna be surrounded by the water molecules to the least extent. Whereas this fluorine ion that you are having, it has possessing the high charge density. It has high charge density. So due to that, it's gonna be maximum solvated. So if you see the ions, solvated ions, the sizes if you compare, that is gonna be fluorine is gonna be of the maximum followed by the fluorine. Then you have is bromine and least you are gonna have it for the sulfate ions. Right? Now if you see the mobility that is inverse of this sizes of the solvated ions. So fluorine negative it's gonna have the least followed by the fluorine. Then you have the bromine and the maximum one it's gonna be for the sulfate ions. So this is gonna be the order that you are gonna observe for the conductance. Alright. So sulfate, then the bromine, then the chlorine and the fluorine that is given to us in the option C in this case. Right. Moving upon to the next one, we have is this question. It says at 291 Kelvin the ionic velocities of the Ag positive is this much and that of the nitrate ion it is this much centimeter per second. If the specific conductivity of the point 1 normal AgNO3 solution it is this much, then what is the degree of the dissociation at this dilution? So again, you need to find is the alpha value, which is the ratio of the molar conductivities at some other conditions and the molar conductivity at the infinite dilution, right? So now we from the velocities we need to find the conductivities. To find the this conductivity at the infinite dilution you need to find of this AgNO3. We need is the conductivity of the Ag positive at the infinite dilution and we need is the conductivity of this nitrate ion, conductivity of this nitrate ion at the infinite dilution. This is what we want, right? So the conductivity of the Ag positive at the infinite dilution, this is equal to the mobility of it. This mu is its mobility into the Faraday's constant. Alright. So where you have been given its value that is of the ionic velocity which is for the Ag positive at 0.00057. Multiply this with the Faraday's constant, we can find its conductance at infinite dilution which is of the 55.005. Alright. And the similar way the conductivity at the infinite dilution for the nitrate ion, it's gonna be multiply it with the speed that is 0.00063. Multiply this with the Faraday's constant that is 96500. We will be getting the value as 60.795. Now, the conductivity at the infinite dilution, you can find this. Just substitute these values now. That is 55.005 plus of the 60.795, which is gonna come out to be as 115.80. Okay, so this is gonna be the conductance at the infinite dilution. Now we need is the conductance at the other conditions also. For that we have been given the concentration value and also the specific conductance value it is given to us. So the lambda n, it's gonna be kappa into the 1000 upon the concentration. So here this 1000 factor is included based upon the units of the concentration and the units of this kappa that is given to us. So here the kappa is given to us to be 0.00947, 0.00947. It's in ohm inverse, centimeter inverse. Okay, and the concentration that is given to us, it is in the normality it is given, molarity also if you will be taking, so the unit charge is 1 only, normality and molarity are gonna still remain to be the same only, so it is zero point 0.1 molar or the normal solution you are having. So suppose it is mole per liter, we will be having it, mole per liter. Now to convert this liter into the centimeter inverse, that is in the centimeters if you want to bring it, so that the units it becomes the similar, it's multiplied with the factor of the 1000 over here. Okay, so for that unit conversion, this 1000 factor is added in this case. So solving this, the value of the lambda n, we will be getting it as 94.7. The value you will be getting it. That will be in the Siemens centimeter square per mole inverse. Okay, so this is the units you will be getting. Now the alpha value, it is lambda n upon the lambda m at infinite dilution, that is gonna be 94.7 upon, at the infinite dilution the value is 115.80, 115.80. So the value we will be getting it as 0.81. So this is gonna be the alpha. So this was a new type of the concept that was introduced, that to find firstly for the ionic species the infinite dilution values of the conductivities, we have to find this out. So for that you need this speed, it will be given, multiply it with its Faraday's constant. You will be getting the infinite dilution, then add both of these ionic conductance of the particular ions, will be getting the conductance at infinite dilution, and from the other data at the other temperature conditions, what is gonna be the value of the conductance, that we can find it out, and taking the ratio we can find the value of the degree of the dissociation. Okay, now the next question we have is this one. It says the plots of a given conductance versus the square root of the concentration of two of the electrolytes are given below, with the lambda naught, that is equivalent conductance at the infinite dilution. Which of the following statements is the correct one? So we have to depict that which plot is for which of the electrolyte solution. So we know for the weak electrolyte solutions, we cannot extrapolate the graphs, but for the strong electrolytes, extrapolation can be done when you have this type of the plot, that is for the conductance versus the root of the concentration. So this is gonna be for the, this is for the strong electrolytes. That is extrapolation can be done and we can find the infinite dilution. But for the weak electrolytes, its extrapolation, if you will be doing it like this, it's gonna go in the parallel direction only. We cannot find the lambda naught at the infinite dilution for this one. This is for the weak electrolytes. Okay, so the plot 1 is for the strong electrolyte. The first statement is saying it's for the weak electrolyte and second is for the strong. This is the incorrect. Second is extrapolation to the lambda naught as shown in the plot 1. It cannot be done. No, it can be done. That is for the strong electrolyte. C is saying extrapolation to the lambda naught in the plot 2. It cannot be done to get the correct lambda naught, that is at the infinite dilution. This statement is true, that in the second one you cannot do the extrapolation to get the infinite dilution value. So this is gonna be the correct answer. Okay. Next is we have this question. Again the statement reads, it says consider the following statements for the electrolyte solutions which is diluted to approach infinite dilution. Statement 1, it says ion-ion interactions are reduced to effect the increase in the conductance. This statement is true. That is for the strong electrolytes. This scenario you are observing here only you can see it, that as you are decreasing the concentration, the conductance value it is increasing like this. As you go from this concentration it is decreasing, The conductance value it is increasing. Reason for the strong electrolyte is that with the dilution, the strong electrolytes, the cationic and the anionic species, a lot of electrostatic forces interactions were present. But with the dilution, the water molecules they will start coming in between them. Due to that ion-ion interactions it's gonna break and the conductance it is gonna increase in that case. Okay. And the next statement it says the number of the ions gets increased to affect the increase in conductance. This is true for the weak electrolytes. This is for the weak. This one is for the strong electrolytes. Here also you can see it again in the second curve. This increase, a sharp increase, you are observing it at this particular point as you are decreasing the concentration. The reason for that it lies in the fact that the number of the ions, because weak electrolytes they show the partial dissociation. As we do the dilution of it, that is the concentration it is decreasing, increase is observed because the number of the ions it is increasing in that case. Okay, so the first one is for the strong and second is for the weak electrolytes. So it says which one of the following is the correct, we have to find it out. Option A, it says both the statements are for the strong electrolytes, incorrect. Next is both are for the weak electrolytes, again you are incorrect. It says first one is for the weak electrolyte, second is for the strong. This is again incorrect. Reverse statement is given. D, it says first one is for the strong and second is for the weak electrolytes. This one is the true statement. So D is the correct answer in this case. Okay. Next is we have this question. It says the value of the log gamma plus minus in the Debye-Huckel limiting law for a this much molar KCl solution in water. Okay, so we know according to our Debye-Huckel limiting law, my log of the gamma plus minus it is equal to the minus of 0.509 into the charges, that is Z plus and the Z minus, into the root of this ionic strength. Right? I is my ionic strength. Ionic strength, which is equal to the half of the Ci into the, this is summation it is there, summation of half of the Ci into the Zi square. Now what is the Ci and the Zi? Ci is the concentration of the ith ionic species and Zi is the charges present on that ionic species. Here we are having is the KCl, which is gonna furnish the ions, that is K positive and Cl negative. If KCl is of this much molality we are having it, the K positive concentration it's also gonna be 0.01 molar, and for the Cl negative also it's gonna be 0.01 molar only. Right? So now if I find the ionic strength in this case, it's gonna be half into the for the potassium ions, the concentration is 0.01. Charge is the plus 1, its square it will be there. And for the Cl negative, it's 0.01 into the minus 1 square. We will be getting the concentration as 0.01. This is the ionic strength value we are getting it from here. Okay. Next is log gamma plus minus. It is equal to your minus of 0.509 charges, that is Z plus and Z minus, it is plus 1 and the minus 1, its mod we have to take it into the root of the ionic strength, that is we have found out that to be as 0.01. Right, so just solve this. Minus of 0.509 into the root of the ionic strength, which is 1 by 100. So solving this 1 by 10, it will come outside. That is equal to minus of 0.0509. That is equal to the log of gamma plus minus. This is gonna be the value. So what we wanted to find it out, the value of the log of the gamma plus minus only, that we have got it as minus of the 0.0509, that is in the option B over there. Okay. Next is we have this question. The plot that it indicates the conductometric titration it is between. So initially you can see you are having the higher conductance. As you are increasing the conductance, as you are increasing the volume of the base, the conductance it is decreasing. Right? And after this particular point, this is your equivalence point, you can say, or the end point. After that, the conductance, it is not increasing. So that scenario will be there when we are having the weak base, because if strong would have been there, after this particular point the conductance would have increased. So this is for the, this indicates here is my weak base I am having it. And the initially we are having the higher conductance value, that represents it is for the strong acid we were having it. That is why the concentration in the conductance it was higher initially. So the plot is for the strong acid versus the weak base, that is given to us in the option B over here. Okay, moving upon to the next one, we have is this question. It says consider the following conductometric study reaction between the KCl and the AgNO3. So what is happening in the PQ region? Okay. So we are having this now KCl, and along with that you are having this AgNO3. Both of them, they will be combining and forming the AgCl, and along with that the KNO3 it is being formed. Right? So AgCl, it's gonna form the precipitate and it's gonna settle at the bottom. So in the PQ region, what is basically happening? In the starting, we are having is the KCl, and with the due course of time, AgNO3 is being added over there. So the PPTs of the AgCl are getting being formed in this particular region. At the point Q, all the PPTs would have been formed. Alright, so we are having the beaker like this. Here is the KCl, you are having it, and from the burette, with the help of the burette, this is the burette, AgNO3 is being added over here. AgNO3 is added. So we are adding it drop by drop, so PPTs are getting being formed. So in this PQ region, the PPTs are being formed until the point Q. Both of these ions, they will be equal in the number, that means equivalence point you will be having it. And after that, this increase you are observing because the AgNO3 you are adding it into the excess. Due to this, the increase in the conductance you will be having it. So in the PQ region, the precipitates are getting being formed, and also if you see the Cl negative ions that you are having, it's getting being replaced by the nitrate ions. So in the KCl it was present. Now it's after that it's forming the KNO3. So chloride ions and the nitrate ions, both of them they are large in size. That is why not much change in the conductance you have observed in the PQ region. Okay, so Cl negative and the nitrate are also being replaced, are replaced. That is why change in the conductance. Along with that, the PPTs of the AgCl are also getting being formed. Due to that, also the conductance value has not shown a much change in the PQ region. Okay, so the correct answer it will be that precipitation of the AgCl and the replacement of the chlorine by the nitrate is taking place. That is given to us in the option C over here. Okay, next is we have this question. So consider the following plots for the conductometric titrations. So you have to find this out, that which of the plots is for which of the titrations, that is for the weak acid, weak base, or which type of the acid base, the conductometric titration curve you are getting it. In the plot number 1, if we see, here you see initially you are having the low conductance, it is there, right? This is the low conductance, and afterwards the conductance after the end point when you are seeing it, the conductance value it is increasing. That means initially the low conductance it represents that weak acid we were having it. This is weak acid. And afterwards this conductance value it is increasing, which represents the strong base or the strong alkali we are having it. That is a base which is soluble in the water, that is called as your alkali. So the first plot is for the weak acid versus the strong base. Whereas the second one, if I am seeing, here also the conductance value is very low, right? And after the end point also, the conductance value it is not increasing, which means this is again your weak base only. This is weak base, and this one is also your weak acid only. So weak acid versus the weak base is the plot in the second one, and the first one it was your weak acid versus the strong base. So the plot one, option A says for the weak acid versus the weak alkali. This is the incorrect one because it is increasing after the end point. So it cannot be the weak alkali in this case. Second one, it says it's for a strong acid versus a strong alkali. If this would have been the scenario, the initial conductance would have been high in that case. So this is also my incorrect. Next is plot 1 is for the AgNO3 versus the HCl, and the plot 2 is for the AgNO3 versus the KCl. This is also not the scenario. So this is your incorrect. D option, it says it is for the weak acid versus the strong alkali, and plot 2 is for the weak acid versus the weak alkali. This one is the correct, and the correct matches the option D in this case. Okay. Next is we have this, which is two electrolytes you are having. One is this AX and other we are having is this BX. They were chosen to determine the transport number using the moving boundary method. So using the moving boundary method, we are finding the transport number. It is given to us, two of the conditions have been given to us, that the cation B, it moves slower than that of the cation A, and the electrolyte Bx, it is denser than that of the Ax. So in the moving boundary method that you have, the cationic species, two of the electrolyte solutions that you are using, one is called as the indicator electrolyte and other is the electrolyte in which the ionic species whose transport number we want to find it out. So here we have is one is the indicator electrolyte indicator and other is the desired electrolyte, you can say it desired electrolyte, that means the cationic species whose transport number we have to find it out. Okay, so the condition in the moving boundary method is that here the indicator electrolyte that I am using, here also it is gonna have the cationic as well as the anionic part. This is gonna have the cationic and the anionic part, and the desired electrolyte solution, this is also gonna have some cationic and the anionic part. This is also have some cation and the anionic part. So the condition is that the cation which is of this indicator electrolyte, it should not move faster than the cation whose this transport number we have to determine. What I say, that the cation which is present in the indicator electrolyte electrolyte, it should not move. It should not move faster. Should not move faster than the desired cation. Then desired cation. This condition it is required. Okay. And also the second condition that we require is that the anionic species that you are having, the anionic species in the indicator as well as the desired electrolyte, it should be the same. Here you can see AX and BX it is given. Here this anionic part is X. Here also this anionic part was X only. So the primary condition, that is the anionic part should be the same, that is getting the satisfied. Okay. So this is the scenario that you wanted. So here we can, from this scenario, you can check it out. Here it is saying that B is moving slower than that of the A positive. That means its speed is less. So it is gonna behave as your indicator electrolyte. Bx will be my indicator, right? Bx is gonna be the indicator electrolyte, whereas the Ax, it is gonna be the desired electrolyte in which the transport number we are going to find this out. Okay, so here it says which of the following statement is the correct. The first statement, it says the transport number of the A positive, it can be determined if Ax is used as the principal electrolyte and Bx is used as the indicator electrolyte. This statement is the correct because B is moving at a slower speed. So Bx is gonna be a indicator electrolyte, whereas Ax is gonna be the desired electrolyte that is called as the principal electrolyte. So this statement is your correct over here. You can check the rest of the statements also. In the second, it says the transport number of B positive it can be determined if AX is used as the indicator. This cannot be there because it is condition is given that B positive it is moving slower. So BX will be my indicator and not the principal. So this is the reverse. It cannot be there, right? In the similar manner, transport number of X negative it can be determined if AX is used as the indicator and BX as the principal. Again, the reverse thing is given, so can't be that. Next is transport number of A positive, B positive, X negative can be determined if AX is used as the principal and BX is used as the indicator. Again, this can't be there. Only for the A positive you will be able to determine the this transport number you will be able to determine, and subtracting that from the one you can find it for the X negative, right? For the cationic and the anionic species, for the principal electrolyte you can determine the transport numbers but not for the indicator one. Okay, so A is the correct answer in this case. Moving upon to the next, we have is this. It says, which of the following statements about the electrolytes is or are the correct one? The first statement it says conductivity of the solution. It depends on the sizes of the ions. This is your true statement. We have been seeing that the lithium positive, sodium and the potassium, the solvation it is taking place due to that their sizes it differentiates and that affects the conductivity. So this is my true statement. Next is conductivity. It depends upon the viscosity of the solution. Again, it is the true. That is, suppose you take one of the ions in one of the solvents, suppose the water you are taking, and the other next time you take the same cationic species in some other solvent, suppose CCl4 you will be having, the conductivity value is gonna be varying. Right? Next is conductivity. It does not depend upon the solution of the ions present in the solution. It says does not depend. It is your incorrect because we have been seeing the solution it affects the conductivity. Right. Next is conductivity of a solution. It varies with the temperature. It is also your true one. So first, second, and the fourth are the correct. That is given to us in the option C in this case. Right. We have is this. It says statement based it is there. Statement 1 it says near the lower value of the concentration, the molar conductivity of the acetic acid it increases sharply on the dilution. And the statement 2 it says the limiting molar conductivity it is obtained by the Coleridge law of the independent migration of the ions. So here if you see, it is saying the statement 1 the near the lower value of the concentration, the conductivity of the acetic acid it increases sharply. So here from the curve that we have seen, the two of the curves we saw now, for the strong electrolyte and for the weak electrolyte. For the weak electrolyte, if you see at the lower value of the concentration when you are doing a sharp increase in the concentration, sharp increase in the conductivity you are observing it for the acetic acid, that is your weak electrolyte. Reason for that it is on dilution the number of the ions it is increasing. So this statement is the correct one. Next is for the limiting molar conductivity. By extrapolation, we were not able to solve it by using the Coleridge law. That is, the conductivity it is independent of the migrating ions. This law is used to find the conductivity of the weak electrolytes at the infinite dilution. So this is also your correct one. Right? So both these statements 1 and 2 are the correct. So the correct answer it becomes the option A in this case. Okay. Next is this one. Which of the following statements is correct with respect to the ionic mobilities in the solution? The first statement we have is ionic mobility in the solution. They have a similar magnitude as that of the speed of the gaseous molecules in a gas. Okay, so ionic mobility of the ions solution, they are of the different magnitudes. Obviously, if you are taking some ions in the solution and you are taking it into the gaseous medium, their conductivity is gonna be different. So this is not gonna be the correct one. Next is, it says solvation. It increases the ionic mobility in the solution. How is that possible? With the solvation, the ionic mobility it is gonna decrease, right? Next is sodium ions. They have the low ionic mobility due to extensive hydration of the sodium positive ions in the aqueous solution. This is your correct statement, right? Next is ionic mobility. It reduces the degree of dissociation of the strong electrolytes in the solution. This is not the correct. C is the correct answer in this case. That is for the sodium ions. Due to their extensive hydration, being smaller in the size, they get dehydrated in the solvent in the aqueous medium. Due to that, their ionic mobility it is decreasing. Right. Next is this. It says which one of the following statements is not true, not the correct in relationship to the Debye-Huckel theory of the electrolyte solution. Not the correct one. Okay. The Debye-Huckel theory it assumes the ions in the solution to be in the constant motion. This is the true one. The next is the Debye-Huckel limiting law. It is applicable for the concentrated solutions only. This is the incorrect one. From the name only you see, it is saying that it is your limiting law. That means it is reaching a limit to the infinite dilution. So how it can be applied to the concentrated solutions in that case, right? The incorrect statement is the option B only, right? Next, it is saying the ionic strength of the solutions, it does not depend upon the dielectric constant of the solution, the solvent. That is also the true over here. The ionic strength, if you see, ionic strength is half of the Ci into the Zi square. If summation it is there. It's dependent only on the concentration and it is dependent upon the charges. It's independent of the dielectric constant of the solvent that you are taking it. Next is Debye-Huckel limiting law. Plots for the NaCl and the KCl it should be identical. So you see, according to the Debye-Huckel limiting law, log of gamma plus minus it is minus of 0.509 into the Z positive Z negative root of the ionic strength. So here just the charges of this it is getting being involved for the sodium chloride and for the KCl. Both of them they carry the 1 unit charge only. So the same plot you are gonna observe in them. Right? Because nature of these ions it is not involved in this expression. Okay. So this statement is also your true over here. So C B is the correct, that is the incorrect statement in this case. Next is we have this numerical. It says that in a conductivity cell of a cell constant 0.003 centimeter inverse concentration of this much molar solution of the acetic acid, resistance against the ionic mobility is this much at 25 degrees centigrade. Degree of dissociation, alpha value you again have to find it out, and at the infinite dilution, the conductance value it is given to us. So alpha we know it is lambda m upon the lambda m at infinite dilution. So molar conductance it is equal to the kappa into the 1000 upon the molarity. Then concentration it is mole per centimeter cube. This 1000 factor you have to include at that case. Okay. So we have been given is this cell constant and this resistance value, this kappa value we have to find this out. We know that R is equal to rho L by A. 1 by rho which is equal to the specific conductivity, it is 1 by R into the L by A, that is gonna be equal to 1 by 20 ohm into the 0.003. This is in centimeter inverse. So kappa value we will be getting it as 1.5 into 10 raised to the power of minus of 4 ohm inverse centimeter inverse. Right. Now the lambda n It's gonna be kappa into the 1000 upon the molarity. Kappa value is 1.5 into 10 raised to the power of minus of 4 ohm inverse centimeter inverse into the 1000 upon the concentration, which is given to us as 0.01 molar molar concentration you are having it. So solving this, we are gonna get the value as 15 into the 10 raised to the power of minus of the 4 ohm inverse meter square per mole inverse. This is the value you will be getting it. Now the alpha value when you will be finding, alpha value is lambda n upon the lambda n at infinity, that is 15 into 10 raised to the power of minus of 4, here it is 390 into 10 raised to the power of minus of 4, we will be getting the value as 0.038. Okay, so 0.038, that is in the option C we are having it. Right. Next is we have this question. Again the numerical based question you are having it. So here it says the specific conductance of the saturated solution of a sparingly soluble salt AgCl in the water at 25 degrees centigrade after subtracting the specific conductance of the pure water is this much. So kappa value is given to us. What will be the approximate solubility of the AgCl at this temperature given that the molar conductance at infinite dilution we are having is this much. Okay. So we know this thing that where the kappa value it is given, which is 1.82 into 10 raised to the power of minus of 4 ohm inverse meter inverse, and the lambda n it is given as 1.38 into 10 raised to the power of minus of the 2 it is given to us. We know that lambda n it is kappa upon the concentration. So kappa value it is given to us as 1.82 into 10 raised to the power of minus of 4 ohm inverse meter inverse, and here we have the concentration one, this not the concentration, this value that is of the lambda n, you can bring it downwards. Here the concentration you have to find this out. So concentration it's gonna be 1.82 into 10 raised to the power of minus of 4 ohm inverse meter inverse upon this lambda n value, which is 1.38 into 10 raised to the power of minus of 2 ohm inverse meter square per mole. Right. So with this ohm inverse will get cancelled out. So mole per meter cube, the value we will be getting it as mole per meter cube, that is 0.0137 mole per meter cube, the value we will be getting, that we can write it as 1.37 into 10 raised to the power of minus of 2 mole per meter cube. So that is given to us in the option A over here. Right. Next is we have this question. It says which of the following statements regarding the conductometric titrations including the acid and the bases is or are not the correct. Incorrect statements you have to find. In each of the cases, alkali or a base is added to the acid contained in the conductivity cell as the titration it progresses. Okay. It says the electrical conductance, it depends only on the mobility but not on the number of the ions. How is that possible? It is dependent upon that. So this is my incorrect statement. Next is the titration of a strong acid and a strong base. It yields a V-shaped plot. This statement is the correct one. Next is titration of a strong acid against a weak base, and a weak acid against a strong base is identical in the shaped plots. How it can be true? For a strong acid like this, initially you will be having the higher conductance and then the plot it is gonna become like this. This is when you have strong acid plus the weak base. This type of the plot makes this weak acid with a strong base. So initially if you are having a weak acid, its concentration is gonna be lower one you will be having. Like this the plot something you will be getting. This is for a weak acid plus the strong base. So how it these both are identical. Initially only you can see conductance value. These are your huge differences there between these two. So this is your incorrect one. Next it says in a titration which is involving a mixture of strong acid and a weak acid, firstly we against a strong base, the strong acid is neutralized first. This statement is true. Like this the plot we observe. Initially, suppose if you have HCl and the acetic acid mixture you are having and you are treating it versus the NaOH. So initially this H positive ions that is from the HCl, they will be coming like at this point the neutralization of it will take place, then at this point the neutralization of the weak acid it will start, and after that the NaOH conductance is gonna come. So initial one, this is because of this HCl, this is because of this acetic acid, and after that the NaOH conductance it is gonna take place. Okay, so this is for the conductance versus the volume of NaOH. Okay. So firstly the HCl is neutralized, the statement is the true. So the incorrect one we are having as first and the third one. So that is in the option B over here. Okay. Next is you have this. It says consider the conductometric titration curve for the HCl versus the NaOH. So various points have been mapped. So initially at the point A, we will be having only the HCl, right? In the region that is from A to C, if you observe, HCl and is being treated with the NaOH, where the HCl is treated with the NaOH, giving us the NaCl and the water. Right till the point C, this reaction is gonna proceed. At the point C, we will be having the equal amount of this HCl and the NaOH. Their moles it will be balanced, and after that we will be having the NaOH. Due to that, this conductance increase we are observing it. Okay, so here it's asking is about these points. So which one of the following is not the correct is in the present is in the respect of the given conductometric titration curve. Statement 1 it says at the point B, the solution contains a mixture of HCl and the NaCl salt. So its statement is correct. You can see in the region from the A to C till the end point is achieved, B is lying in between. Here we will be having the HCl as well as this NaCl formation that is taking place. Okay, here initially this NaOH it is less, but the HCl amount it is higher one. That is why this reaction it is proceeding. So this statement is your true one. Next is at the point C, the solution contains the mixture of HCl and the NaCl salt. So here at this point, complete neutralization has taken place. It's not you will be having the HCl present over here. Here the reaction it has completed. Your NaCl and water only it will be present, but HCl it won't be present at this point. So this is my incorrect one. Okay. Next is at point E, the solution it contains a mixture of where the instead of HCl, where the NaOH it will be present. Mixture of NaOH and NaCl it will be present. So this statement is your true over here. Reason being, if you see after the end point when you are going, so here the NaOH we have added, and after the neutralization this NaCl was being formed. So this NaCl is present and this NaOH it will be present. Okay. Next is at point A, the solution it contains HCl only. This is the true statement. At the beginning we were having only the HCl only. So the incorrect statement is the option B in this case. Okay. So this correction you just make it that instead of the HCl here the NaOH effect is present. Right? So I hope this one is clear. Moving upon to the next one, this question you are having. Okay. It says what will be the transport number of the ions in the aqueous solution of this much molar HCl using a moving boundary method. So again you see this is the third question that you are encountering from your moving boundary method. So make sure you study this topic very well. Okay. With the cadmium chloride, it is that the indicator electrolyte. Here the boundary it moves by this much distance with the cross sectional area is this much upon flowing this much Faradays of the electricity in the current, that means charge value it is given to us. So we know transport number for the cationic part, this is equal to the area into the length into the concentration into the Faraday upon the charge value. Right? So just substitute the values now. Area is given to us as 2.5 centimeters square. Length is 7.5 centimeters. Concentration it's given to us as 0.050. It is molar. That means it is in mole per liter. You have to do the conversions in the centimeter so that these units they will get cancelled out. The next is with the 96500, right? This much is the Faraday's constant. Q value we have it is 1.1 into 10 raised to the power of minus of 3 over here. Okay. So now this you will be doing the conversion that is in the mole per liter, bring it to the centimeter. For that, what you will be doing it, multiply this with the factor of 10 raised to the power of minus of 3. This will come out to be in the mole per centimeter cube. Okay. So with this centimeter cube, this centimeter terms it will get cancelled out. With 10 raised to the power of minus of 3, this will be getting cancelled out. The transport number of the H positive, we will be getting it as 0.85. This is gonna be the value. So the answer is the option A over there. Okay. So this formula, just remember this one and the conditions for the moving boundary data is what should be the speed of the ions that are present in the indicator electrolyte and the desired electrolyte, their cationic speeds, how it should vary, and what are the conditions. These are the questions which are important from your boundary method. Okay. Next is this one. If the limiting molar conductance of the barium and the chloride ions are this much and this much, what is the molar conductance at infinite dilution? Very easy. BaCl2, it's gonna dissociate to give the barium 2 positive plus 2Cl negative. So molar conductance at infinite dilution for the barium chloride, it's gonna be the sum of the molar conductance of the barium 2 positive plus 2 times the molar conductance at infinite dilution for the chloride ions. So it's gonna be 127 plus 2 into the 76, which is gonna come out to be as 127 plus 152, that is 279 Siemens centimeter square per mole inverse. Centimeter square per mole inverse. This is gonna be your answer. So here if you see the units are in the meter square it is given to us. So convert this centimeter into the meter now. So 10 raised to the power of minus of 2 in the meters. Square you will be doing it. Here the mole inverse. This is 279 into 10 raised to the power of minus of 4 Siemens centimeter square. Sorry, instead of centimeter we have made the conversions to the meter. Siemens meter square per mole. This is gonna be the answer. 279 into 10 raised to the power of minus of 4, that is in the option B over here. Okay. Next is this one. It says which one of the following solutions it has the least value of the conductivity. So here if you see the concentrations of the electrolytes are given us to be the same, but the electrolytes are different. Here you have the sodium sulfate, potassium, potassium chloride, hydrogen chloride, and the acetic acid. Acetic acid is my weak electrolyte. So weak electrolyte is gonna dissociate partially only, so its conductance is gonna be the least. Right. Next is this one. So this question I'm leaving for you for the while. In the next part, we will be doing the discussion about this question, and for the remaining questions that is also we are still having. Okay, because the video is becoming the lengthier one. For the meanwhile, you just try this question and do let me know the answer in the comment section. We will be discussing the solution to this one in the next class. Okay, so this one is your homework kind, you can consider it. In the next class, we will be doing the discussion of it. Also, if you want more of the questions, I can get till we reach into the next part. This question is there. This also you can consider. Take the screenshot of it and just try to solve it and give me the answer in the comment section. Okay. So the remaining ones we will be discussing in the next part now. So I hope all the solutions that we have discussed in this part is clear to you. But if you still have doubt at any of the questions that we have discussed so far, you can ask me in the comment section. I'll surely reply to that. Okay, and make sure these two questions that I have given for the homework, you try it firstly yourself, then look upon to the answer. Okay, so that is it for this part now. We'll be meeting you in the next video with the solutions to this one and the further questions. So till then, bye bye.